I am Amrita from Department of Electronics and Communication Engineering, and my topic for signals and stochastic processing is linear time variant system. Introduction to LTV systems. Linear time variant systems are crucial in control theory and signal processing. They differ from linear time invariant systems by allowing changes over time. Understanding LTV systems is essential for analyzing real world systems that evolve. Defining LTV systems. LTV systems are characterized by their dependence on time varying parameters. The system's output is influenced by both the input signal and the time at which it occurs. This introduces additional complexity in analysis and design compared to LTI systems. Mathematical representation. The general form of an LTV system can be expressed using differential equations. The output can be represented by the convolution integral with time varying coefficients. This mathematical representation highlights the system's dependence on time. So, in the right side we can see the separable differential equation as an example. So, the dy by dx equals to f of x into g of y, and in the second equation where the g of y comes down, dy by g of y equals to f of x dx. After this, we will separate the variables and we will do the integration. So 1 by gy of dy equals to integral of f of x of dx. This is the separable differential equation. Examples of LTV systems. Common examples include systems with time varying gains or filters. Adaptive control systems that adjust parameters based on performance are LTV systems. Communication systems that change over time due to varying channel conditions also qualify. These are the examples of LTV systems. Time varying parameters. Time varying parameters can include coefficients that change due to environmental factors. These parameters can be deterministic or stochastic, impacting system behavior. Identifying these parameters is critical for accurate system modeling and prediction. System response analysis. Analyzing the response of LTV systems require specialized techniques, and the time domain response can vary significantly based on input and time. Frequency response methods can also be adapted to account for time variance. So this is the graph between, in the right side we can see the graph between c of t and t, where t is a time, and here there are two parts, transient state and steady state. Transient state is for the linear state where the curve goes increasing, and coming to the steady state the curve comes to the steady and makes the constant time. Stability in LTV systems. Stability analysis in LTV systems is more complex than in LTI systems. Time varying elements can lead to conditions that compromise stability. Tools like Lyapunov method can aid in assessing stability in these systems. Bibostability of LTV systems. A. A system with impulse response. B. A system with state-space equation. So here are the two equations we can see. One of the equation with impulse response and another one is with the transition matrix. Control strategies of the LTV systems. Control strategies must adapt to the time-varying nature of LTV systems. Adaptive control and robust control techniques are commonly employed. These strategies aim to maintain desired performance despite system changes. And here we can see the time domain and the frequency domain. Where the time domain we can see the signal amplitude versus the time, and here frequency domain we can see the discrete time intervals. So whereas in time domain we can see the continuous time intervals and some of the different intervals. Coming to the applications. Applications of LTV systems. LTV systems find applications in telecommunications, robotics and aerospace. Adaptive filtering in audio processing is a prime example of LTV utilization. Many modern technologies rely on the principles of LTV systems for performance. LTV system simulation. Simulation tools are vital for studying LTV system behavior. Numerical methods such as Runge-Kutta method are often used for time domain analysis. So we use the Runge-Kutta method for the time domain analysis. Simulations enable engineers to visualize system response under various conditions. So here we can see three ways to calculate the LTV. The customer lifetime value gives the average monthly revenue per customer into customer lifetime in months, or average monthly revenue per customer by monthly churn, or the average order value into number of repeated sales into average retention time in months. So these are the three ways to calculate LTV. Comparison with LTI systems. LTI systems differ fundamentally from LTI systems in their time dependence. So these LTV and LTI system depends on their time because they are different from their time dependence. While LTI systems assume constant parameters, LTV systems do not have. So this time LTV means linear time variant do not have the constant parameters as the time is varying. So these full linear time variant and LTI systems both differs only on their time. This distinction leads to different approaches in analysis and design. So here we can see the logic diagram of the LTI system. Time varying inputs. The input to an LTV system can also be time varying, further complicating analysis. Methods for handling time varying inputs include input shaping and prediction. Understanding the input characteristics is essential for effective system response. State space representation. LTV systems can be represented in state space form, aiding in analysis. The state space representation captures the dynamics of the system over time. This framework allows for the use of modern control techniques. Frequency domain analysis. Analyzing LTV systems in the frequency domain requires advanced techniques. Time varying parameters can distort frequency response characteristics. Special methods like the Wigner-Ville distribution can be utilized for analysis. So this frequency domain analysis is measured with time where with the frequency using the discrete time intervals. Challenges in LTV systems. One major challenge is the increased complexity in system identification. The time variance can lead to difficulties in predicting future system behavior. Robustness against parameter variations is a key concern in design. Numerical methods for LTV systems. Numerical methods are crucial for solving LTV system equations. Techniques such as finite difference and finite element methods are often employed. These methods allow for the analysis of complex time-dependent systems. Coming to real-world examples. Examples of LTV systems include automotive control systems, adjusting to speed, and power systems adapting to load variations also illustrate LTV behavior. These examples show the importance of LTV systems in practical applications. Coming to the future directions, research in LTV systems is focusing on improving adaptability and robustness. The integration of machine learning techniques is becoming more prevalent. Future developments aim to create more efficient and reliable LTV systems. Coming to a summary of key points, LTV systems are essential for understanding time variant dynamics in engineering. They require specialized analysis methods compared to the LTI systems. Applications span numerous fields, highlighting their significance in technology. Thank you.